In part one, we're going to talk about inferences for correlation. So the idea is we're going from samples to populations in terms of looking at the correlation coefficient. So earlier in this course, we examined how to find the correlation from a set of data. So you have a population or you have a sample, and you just want to find a correlation in that sample or population. But when we calculate a correlation from a random sample of data from a population, how do we know the correlation isn't just due to sampling variability? Maybe we just got a weird sample. Maybe it's just an unusual sample, and that correlation we think may not exist in the population. Well, we can make inferences about the correlation in population from a sample correlation, just like we've done with other sample statistics such as the mean or a sample proportion. So let's review the covariance and correlation for a sample. The sample covariance between two variables, x and y, it is denoted by COV x comma y with the parentheses around the x and the y. Sometimes it's called S subscript x y. And it's basically just the average of the cross products of x and y. So we take our values of x, we demean them, so we remove that mean of x, and we take our values of y, remove the mean of these y values, we multiply each of these two x and y values together for every single person or every single row of our data set, and we add these values up and then we divide by n minus 1, which is the effective degrees of freedom. So when we calculate covariance, the units are in terms of x and y. So for example, if x were body fat and percentage, and then y were weight in pounds, the units of covariance would be percent body fat times the weight in pounds. In terms of a population, the notation is quite similar. So when you have a population covariance between x and y, we use, you might see it as denoted by COV x comma y with parentheses around it, but more often you will see the use of sigma. So remember, Greek letters refer to population parameters, so we have sigma subscript xy. And then again, it's just the average of the cross products of x and y, except we're dealing with population parameters. But that's because we presumably have the entire population. If, so you take your x values, you remove the population mean, you take the y values, remove the population mean for the y values, you multiply these two differences together for each person or each row of the population, and then you divide by capital N, where N is the total size of the population. Again, the units are in terms of x and y. So when we have a correlation for a sample, what we do is we standardize the sample covariance. So we take our sample covariance and we divide by the standard deviation of x times the standard deviation of y. And often you will see the sample correlation denoted with r subscript xy. So we just take the sample covariance and we just standardize it by dividing by the product of these two sample standard deviations. When we calculate the correlation for a population, again, we're just standardizing the population covariance. So you take the population covariance, all right, and you divide by the population standard deviation times the population standard deviation of y. So these two variables, you just divide by the standard deviations of each. And the Greek letter is rho for the correlation for a population. So just to recap, the correlation coefficient, it's a numerical summary, and it gives both the strength and the direction of a linear relationship between these two variables, unlike, for example, the covariance. Covariance only gives the direction of a linear relationship. It doesn't give the strength. So correlations, they're bound between -1 and +1. So the sign is going to indicate the direction of the relationship. So positive value of a correlation coefficient, that's a positive linear relationship. If it's negative, it's going to indicate a negative linear relationship. If the correlation is 0 or near 0, then we'd say the relationship is quite small and there really isn't much of a linear relationship. The absolute value gives the strength of the relationship. So negative 0.8, that's an absolute value, that's 0.8. That's stronger, the strength of that linear relationship is stronger than positive 0.4. And with that, we've covered the basics of correlation coefficient the correlation coefficient and the sample covariance, population correlation coefficient, and we're ready to talk about how to make inferences with correlation.